CPU scheduling and scheduling algorithm. Introduction to CPU scheduling. Scheduling is a process in operating system that decides which process should run on CPU at a given time. When many processes are waiting, the operating system chooses the next one based on scheduling algorithm. The goal is to use CPU efficiently, reduce waiting time, and making the system work smoothly. The operating system uses scheduling to switch quickly between processes. Need for CPU scheduling. The CPU can handle only one process at a time, but many processes may arrive together. The operating system must choose the right order to run them. Scheduling keeps the CPU busy, reduce unnecessary waiting time, and prevent the system becoming slow. It also improves the overall speed and user experience. It also ensures efficient CPU utilization and fair process of execution. CPU scheduling criteria. To check whether a CPU scheduling algorithm works well or not, we look at few important criteria. Some of the criteria are CPU utilization, throughput, turnaround time, waiting time, and response time. CPU utilization. Keep CPU as busy as possible. Throughput, number of processes completed per unit time. The higher throughput means you finish more tasks in the same amount of time. Turnaround time, total time from arrival to completion of a process. Waiting time, the time spent by process in a ready queue. Lower waiting time means better user experience and faster system. Response time means the time between request submission and first response. Terminologies used in CPU scheduling. Arrival time, burst time, completion time, turnaround time, waiting time, and response time are the basic terminology we use in CPU scheduling algorithms. We can calculate turnaround time by completion time minus arrival time, and waiting time can be calculated by turnaround time minus burst time. CPU scheduler and dispatcher. CPU scheduler. When the CPU becomes idle, the operating system select one process from the ready queue for execution. This selection is done by CPU scheduler, which decides which process should run next. Dispatcher. Dispatcher is responsible for transferring control of CPU to next process by selected by scheduler. It performs tasks such as context switching, switching to user mode, etc. In short, CPU scheduler chooses the next process to run. Dispatcher switches the CPU to that process and start its execution. Types of CPU scheduling. There are mainly two types of CPU scheduling: preemptive CPU scheduling and non-preemptive CPU scheduling. In preemptive scheduling, the operating system can interrupt a running process at any time and give the CPU to another process. While in non-preemptive scheduling, once the process starts running on CPU, it will continue until it finishes. In simple, a preemptive can be an interrupt process, and non-preemptive let the process run without interruption. Types of CPU scheduling algorithm. The purpose of CPU scheduling algorithm is to determine the most efficient order for processors to use CPU, minimizing waiting time and maximizing overall system performance. There are many CPU scheduling algorithms. First come, first served, shortest job first, Shortest remaining time first, round robin, priority scheduling, highest respond ratio next, multi-level queuing scheduling, multi-level feedback queuing scheduling, etc. First come, first served. In first come, first served, the process arrives first is executed first. It is simple and easy to implement because order is fixed, but it is non-preemptive, so shorter process may wait unnecessary if a longer process come first. Here is an example. In this example, the execution order of process will be P1, P2, P3 and P4. Gantt chart can be used to show the execution of timeline of processes in CPU scheduling. As I mentioned above, we can calculate turnaround time and waiting time. Here I have calculated average turnaround time and waiting time. Average turnaround time can be calculated by completion time minus arrival time, and average waiting time can be calculated by turnaround time minus burst time. Shortest job first. Shortest job first. Select the process with shortest burst time first. It reduces average waiting time and is more efficient than first come first served. If burst time of two processes are same, then first come first served scheduling is used. But it can cause starvation if long process keep waiting while short ones arrive. In this example, CPU picks the shortest burst time first. The order of execution become P1, P2, P4 and P3. The calculated waiting time and turnaround time are lower compared to first come first served. Shortest remaining time first. Shortest remaining time first is a preemptive version of shortest job first. If a new process arrives with shorter remaining time, then it interrupts the current process and allows the shorter process to complete very quickly. In this example, CPU switches whenever a shorter remaining time becomes available. The execution order is like this: P1, P2, P1, P4 and P3. The CPU always picks the process with the smallest remaining time. Round robin RR. In RR algorithm, every process get fixed time slice called time quantum. If it does not finish in that time, it moves to the end of queue. This method is fair and gives quick response time for all processes. In this example, the time quantum is 2 units. So the CPU gives each process 2 units at a time. Then it moves to the end of queue. The execution order become like this: P1, P2, P3, P4, P1, P2, P3, P4, P1, P3. It shows equal turn for all processes. Priority scheduling. In priority scheduling, each process has a priority number. CPU runs the highest priority first. It may be preemptive or non-preemptive. The main issue is starvation for low priority process. In this example, CPU chooses process based on priority values. So the execution order is P3, P1, P4 and P2. Highest response ratio next. It is a non-preemptive CPU scheduling algorithm. Next process is chosen based on the highest response ratio. Response ratio increases with waiting time. So long waiting time process get priority. This avoids starvation and balance performance. Response ratio formula equal to waiting time plus burst time divided by burst time. In this example, the process with highest response ratio is selected first. So the order becomes P1, P3, P2 and P4. It is the order for execution. Multi-level queue scheduling. In this method, processes are grouped into different queues like system process, interactive process, and batch process. Each queue has its own scheduling algorithm. The highest priority queues are always executed first. In this example, Q1 uses round robin and Q2 uses first come first served algorithm. The CPU finishes all process in highest priority order, so the execution order become P1, P2, P3, P4. Multi-level feedback queue scheduling. It uses multiple priority queues with different time quantums. The process starts with highest priority queue. If process exceed its time quantum, it moves to lower queue, and if process wait for too long, then it moves to higher priority queue. It ensures faster response time. In this example, the process starts in top queue and move down based on CPU usage. The CPU always select from highest non-empty queue. The process execution is in this order: P1, P2, P3, P4, P1, P3 and P4. Conclusion: CPU scheduling decides which process uses CPU next. It improves speed and efficiency. No algorithm is perfect for all situations. Each method has strength and weakness. Modern operating system combines multiple algorithms to improve efficiency, fairness and response time.